Uh, Two, we have also got a good deal of understanding now that how light interacts with molecules or atoms, and what happens within the atoms when it gets struck up with a particular light radiation, on the basis of which we have developed our understanding regarding how or what is responsible for the origin of the entire spectrum of light, in which we are going to first focus on the UV visible range. And it goes both ways, as I told you even in the last class, that like valence shell electronic transitions are responsible for emission of radiations which fall in the UV visible range. Similar is the situation when UV visible radiations are striking an electron within a molecule or an atom, then it leads to valence shell electronic transitions. So considering that this much is well received at your end, we will begin with the next portion of understanding something about how the absorption of light is measured. And once you know something about light absorption, then how you can correlate it with respect to quantitative estimations that you are being doing since your graduation. So, okay, before I go further from this point onwards, let me know from your side that would you want me to give you the entire explanation about the laws of absorption, or can I take some liberty and skip some portions which are there in the derivation of the law, considering that you know about it? Yes, am I audible?
Yes, sir.
Okay, so do you think that I should give you the entire explanation about laws of absorption, and then we move ahead as is the courses, or can I take this liberty that I escape some portions? I can ask you questions. I can find out that how good you have uh, an understanding about laws of absorption, and then we can talk about the things in that way. What will you prefer?
Explaining it would be fine, sir.
Okay, so let's move ahead. I will find out in the course that in the course of our discussion that how good is your understanding about laws of absorption. uh, okay, just give me a moment. I will be resuming in 2-3 minutes. Okay, so the first law of absorption, that absorption of light, that was given is called as the Buger-Lambert law, and it talks about that the amount of light absorbed. That means the statement of the law goes like this: that the amount of light absorbed by the absorbing material is directly proportional to the thickness of the absorbing material and is independent of the intensity of incident light. So, do you remember this law, first of all? Yes?
No, sir.
Okay, you don't remember the law. Okay, this is the first law of absorption of light, which talks about how the light absorption by the absorbing material is proportional to the thickness of the absorbing material. I believe that you might have heard about this law previously, at least. Yes.
Yes,
Yes.
sir.
Okay. So if I try and explain this to you in giving you some examples, then the best possible example that can be given is this, which tells you that when say consider that 100% of the light radiations are falling on the first sample, which you have kept in a beaker. Consider this, then it is the thickness of this beaker or the absorbing material that is going to decide the extent of absorption. If the thickness is more, the extent of absorption would be more. Now, a common example that I give students for understanding this clearly is something like this. Consider that you have a colored gelatin sheet with you. Have you seen those colored gelatin sheets which are available in the market?
Yes, sir.
Okay. So consider that I am holding one, say, red colored gelatin sheet, and you are supposed to look across the gelatin sheet. Imagine that the light source is behind it and you're looking for the light coming through the gelatin sheet. It will appear red, right?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Now imagine that I'm putting, say, two gelatin sheets in between, or three gelatin sheets, or four gelatin sheets. What will happen to the to the light that is coming to you, according to you? Will it still
The
appear red?
amount of light is decreases.
Yes. So will it still appear red, or will it change the way it was previously when I was holding a single gelatin sheet compared to when I am holding, say, 5 or 10 gelatin sheets in the path of light? What is the difference?
It will be deeper red.
Yes, it will be dark red. When we say dark red, then the term itself tells you that anything that is dark has less light, right?
Yes, sir. Yes,
So
sir.
exactly in the same analogy, when we are talking about light passing through, now why this has happened is essentially because when I'm putting more than one gelatin sheets in the path of light, I'm actually increasing the thickness of the absorbing material. Now I hope that you know this, that when we are talking about visible light, okay, before I go any further, can anybody tell me why do you see a particular color to be of that color? Like, say, for example, we were talking about red gelatin sheet. Why do you see it red?
Because the red gelatin sheet absorb the all component of the color and accept the red, which transmitted.
Yes, exactly. So, can I put it like this, Harshit, that it absorbs all other visible colors except red, and it is allowing the red light to pass through. That means it only allows the transmission of red light, while all other visible colors are absorbed to certain extent. So is it good enough if I put it like that?
Yes,
Yes,
sir.
sir.
Okay. So in
Yes, sir.
considering this, that each gelatin sheet is going to have some degree of absorption for light, and is always going to allow that red color light radiations to pass through. What will happen ultimately when we are putting more and more gelatin sheets in the path of light? Lesser and lesser amount of light will be allowed to pass through. You agree now?
Yes, sir.
Yes, sir. Yes,
So
sir.
can we say this
Yes,
reverse way round, that when we are putting more than one gelatin sheets in the path of light, because the thickness of the absorbing material is increasing, hence there will be less amount of light that will get transmitted out. Can I say this?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So based on the same assumption, there was this law that was given and that was proven to be correct later on. So if you look at the same analogy here, imagine this to be the gelatin sheet that you're looking at. So the situation goes like that, the first beaker appears to be the gelatin sheet, and when I'm increasing the number of beakers in the path of light, then the amount of light transmitted will decrease. So other way around, the amount of light absorbed will increase. So if I put it in terms of transmission only, if I plot transmittance on the y-axis and the path length or the thickness of the absorbing material on the x-axis, as the thickness increases, the amount of transmitted light is decreasing, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So I can put it in mathematical relation, which is like I upon I0. Now, I is the amount of transmitted light. I0 is the amount of incident light. Okay, so the ratio of this, the amount of transmitted light upon amount of incident light gives you transmission. Okay, so this ratio is actually transmittance. If I equate it, I can put it like this, that there is an exponential decrease, right? You can see that as the thickness increases, the amount of transmitted light is decreasing exponentially. So I'm putting an exponential unit over here, that is E raised to minus kb. Now where k stands for a proportionality constant and b is the thickness of the absorbing material. Is it fine till now? Should we go ahead from this point?
Yes, sir.
Yes,
Yes, sir.
Okay, good enough. So now we have arrived at a relation which is somewhat like transmittance is going to decrease exponentially as the path length increases. Okay, and the negative sign indicates that there is a negative slope to this decrease in transmittance. Okay, so the next thing that that is about this that we need to focus more upon is that once we arrive at this relation, then we can, in the similar fashion, start solving this relation to get rid of this negative sign and to get rid of that exponential term that we have introduced. So if I take natural log of both sides, then I arrive at this relation. Now, before I go any further, do you know what's the difference between natural log, that is log to the base e, and log to the base 10? The routinely used log value is log to the base 10, correct? And natural log, which is also indicated as this ln, is basically log to the base e. So can anybody tell me what's the difference between the two? Okay, being biology people, we will not be very comfortable with this question, right?
right, sir.
Okay, so I will tell you a very basic difference between these two. Okay, can anybody tell me what is log to the base 10 of 10?
Sir, when there is log to the base 10, we consider its value as 1 when we convert, but when there is log to the base e, then we put 2.7.
No, 2.303 is the value, if you remember. It's
Sorry,
not
sir,
2.
2.2.
Yes.
Yes. So the idea here is, in other way, I can put it like this for your understanding, for everybody's understanding, that when I say log to the base 10, then it means log of 10 is 1. In the similar fashion, when I say log to the base e, log of e would be 1. Do you agree?
Yes, sir.
Okay. So now I'm just putting up log of e is 1, so I can just get rid of that situation if I take log of both sides. So I have got to this relation that natural log of I upon I0 is equal to minus kb. Now, is it fine with you all? how we arrived at this relation?
Yes, sir.
Okay, good. So now if I want to remove this negative sign, now this is a very common situation that biologists are very positive people. So we don't like the negative sign. So we need to remove it. So we actually take an inverse of the log here. So it can be written like the natural log of I0 upon I is equal to KB. Fine.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, if I upon I0 was transmittance, the exact reciprocal of I upon I0 would be absorption, right?
Right, sir.
Okay. So we arrived at this relation that natural log of I0 upon I is equal to KB. So I can call it as absorption. If I want to make it simple, absorption, which is capital A, is equal to K times small b, where small b is the thickness of the absorbing material, or I can say is the path length. Is it fine?
Yes, sir.
Yes, sir.
Yes, sir.
Now, can I put it like this in the previous situation itself, that when we are talking about absorption material, why increase in thickness is actually relating or related to the extent of absorption will act. Okay, what exactly in this absorbing say situation, what exactly is playing a part in increasing the extent of absorption if I say that I'm increasing the thickness? Did you get the question?
So can you repeat?
Okay, fine. So what exactly is involved in the absorbing material's extent of absorption when I'm increasing the thickness of the absorbing material? Yes? Okay. We have developed this concept that absorption is essentially a part which is associated with a molecular entity, right? Molecular or atomic entity. Can I put it like this?
Yes, sir.
Right. So if I am increasing the thickness of the absorbing material, what exactly I'm doing is that I'm increasing the number of molecules which fall in the path of light, right? When the light is passing through,
Right, sir.
right? So other way around, can I not put it like this, that the amount of light absorbed by the absorbing material is proportional to the number of molecules or concentration of the absorbing material?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I can change this rule or law a bit, that okay, it is proportional to the thickness of the absorbing material. But if I say this, that the amount of light absorbed is proportional to the concentration of the absorbing material, then also it will hold true, correct?
Yes, sir.
Yes, sir.
Okay, so in the similar fashion, like we have derived this relation for the thickness of the absorbing material, can I not derive a relation for the concentration of the absorbing material and proportional situation with absorption?
We can, sir.
Yes. So now we have another proportionality constant and concentration being proportional to absorbing material. So can I club these two things together now? Okay. In the similar fashion, like we have derived for thickness, we have also arrived at another relation for concentration proportionality with absorption. Fine.
Yes, sir.
Yes, sir.
So if I want to club these two things together, can I put it like this? Like A is equal to K prime times small b and capital C. Where A was absorption,
Yes,
right?
sir.
K was proportionality constant for path length or thickness of the absorbing material, and K prime is the proportionality constant for concentration. Fine.
Yes,
Yes,
sir.
So can I not come to this relation now that capital A is equal to small a, which is a combination of proportionality constants, small b times capital C. Can I come to this relation now?
Yes, sir.
Yes,
Yes,
sir.
yes,
sir.
So the second law of absorption was about absorption of light proportionality with concentration, and that is called as the Beer's law. And when we combine the two things together, then that means absorption is proportional to path length as well as concentration. Then it will be called as either Beer-Lambert law or Buger-Beer law or simply Beer's law. Fine.
Yes, sir.
Yes, sir.
sir.
About this law of absorption previously?
Yes, sir.
Okay, good. So now we have arrived at this relation, and continuing this discussion further, absorption seems to be directly proportional to concentration and path length, and is linked through a proportionality constant, which is now referred to as absorption coefficient. Okay. So that is what is given over here in this slide, as you can see here. So the same relation I have derived for you. So is there any problem in this?
No, sir.
Sir,
No,
Okay.
sir.
Now the combined law of absorption, or the Beer's law, becomes a combined statement. And what it talks about is the amount of light absorbed by the absorbing material is proportional to the concentration of the absorbing material and to its thickness, and is independent of the intensity of incident light. Is this fine?
Yes, sir.
yes, sir.
Okay. Now, can I put it like this, that the amount of light absorbed by the absorbing material is proportional to concentration only if I keep the thickness constant?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Or reverse way around, can I put it like this, that the amount of light absorbed by the absorbing material is directly proportional to thickness or the path length, provided I keep the concentration constant?
Yes, sir.
Okay,
Yes,
so both ways I can go. Okay. Now there is one thing that perhaps you might not have noticed, but I will bring it to your notice, and you will tell me whether it seems to be applicable here or not. Okay. Now, when I stated for you the first law of absorption, that is the Buger-Lambert law, then in the statement, and now this portion is common in the statement of all laws of absorption. Okay. The statement itself states that the amount of light absorbed by the absorbing material is proportional to the thickness of the absorbing material and is independent of the intensity of incident light. So do you believe that this is valid? Did you notice this? That every time I stated the law, I also stated this, that it is independent of the intensity of incident light. So do you believe that it is actually independent of the intensity of incident light? Yes? Did you get the question?
yes, sir.
Yes, sir.
Okay.
Yes, sir.
So let me solve it for you. What we mean by intensity is basically amount of light,
Yes, sir.
100%.
right? What we mean by intensity is basically amount of light. You agree with me or not?
Yes, sir.
Correct? So when I say it is independent of the intensity of incident light, what I am trying to imply?
That the amount of light doesn't matter in that case.
In the extent of absorption, right?
Yes, sir.
Okay. So let me put it like this. Like we understood something about concentration. Now this is a two entity phenomena, absorption, right? It's a two entity phenomena. Do you agree? That means there has to be an interaction between light with matter, correct?
Yes, sir.
So if I say that the number of matter entities, when it increases, absorption increases,
Yes, sir.
then when the number of light waves will increase, will it not affect absorption? Yes, did you get the question?
Yes, sir.
Okay, now do you think that it is independent of the intensity of incident light? Is the question, do you think that it is important to ask this question? Okay, those who think that this is an important question to be addressed, raise your hands. Okay. But the important thing here is that you should have asked me this question, right? Rather than me putting it for you.
Yes, sir.
If you have understood the concept of absorption and if you have understood the derivation of the law, then is it not valid to ask that when the number of interacting entities is increasing, the process or the outcome of the process should also increase accordingly, right?
Yes, sir.
Do you feel that this statement holds true, that it should be independent of the intensity of incident light?
No, sir.
Alia, you are not audible. Is it for me only or everybody else also feels the same?
No, we heard her clearly. She said
Okay.
no.
Okay. Okay, fine. So perhaps there is a problem from my end. No issues. So if this is so, then why we are putting this sentence then in the statement of the law? See, when we say law, it's a firm rule, right? You cannot break that. You cannot mend that rule as well. So there has to be some way of justifying this. Okay, actually the answer is in front of you. But you are not looking at it like that. Yes, anyone? Okay, anyone is trying to answer or?
Sir, because no matter what intensity of light falls in the substance, it will eventually get reduced.
It will eventually get?
Reduced.
Obviously, it has to reduce when you're talking about absorption, right?
Yes.
And that will happen even when there is a single molecule in the path. Even when, that means there will be reduction. But what we are talking about is that that reduction is proportional to the number of molecules. That's what we just proved. Now, if that
So,
is true, yes, okay, Alia, go ahead.
so it doesn't matter how much amount of light is incident, because our absorbance would always be proportional to the concentration. So it would only absorb as its limit is up to the concentration. So, right? Are you getting me?
I'm afraid I am not very clearly getting what you're trying to convey. Is it the same with everyone?
So the amount of light absorbed
Yeah, right.
depends upon the concentration,
Exactly.
right?
And why does it
So
depend upon concentration, by the way, Alia?
so as you mentioned before,
Right.
I'm
It
sorry,
dep
so I'm having some issue with my mic.
Okay, okay. Go ahead, go ahead. Okay.
So
Yes,
because
Alia.
the number of molecules concentrated within the confined thickness of the material, the surface.
Mm-hmm.
So based on that, the absorbance of light would be proportional to the thickness, as you mentioned, and the said thickness
Exactly.
would always have a concentration, the
Right.
number of molecules. So it
Right.
doesn't matter how much light is incident upon it, it would
Okay.
always have.
Can I put it like this, Alia? You correct me if I'm wrong. It actually depends upon the number of events, right? Absorption events that are happening. Correct?
Yes, sir.
So if I increase the number of molecules, what I'm actually increasing is the chance of the event, correct?
So as in you're increasing the concentration.
Yeah, as I increase the concentration or number of molecules or which are in path of light, I'm actually increasing the chance of the event. Do you agree?
So you're increasing the absorbance, which would lead to
Right.
less transmission.
Absorption is the outcome of the interaction of light with matter, correct?
Yes.
So if this interaction, if I can increase this number of these interactions happening by increasing the chance of this interaction, correct? Or putting it like this, that if I increase the number of molecules which are interacting with light, absorption will increase,
Yes, sir.
correct? So basically what I'm trying to convey here is that if this is true, and if you understand it like this, that it has to happen like light is striking the molecule, right? So if the number of molecules is more, the chance of this event will increase, correct? More number of light radiation will strike more number of molecules. Do you agree?
Yes, sir.
Yes, exactly. So if this is true, then if I increase the other entity rather than increasing the number of molecules, then the chance of the event should also increase proportionately, correct?
Yes, sir.
So if I increase the intensity, then it should also increase absorption. Do you agree?
No, sir.
No, why not? Okay, just put it like, let me put it like this. So say suppose if I write it like, say suppose there are two molecules in the path of light, okay? And there are, say, 1, 2, and 3, and 4 light radiations striking, okay? Now out of these 4, say only one, out of these 4, say 2 strike, so 2 radiations are lost and rest of the radiations pass through, correct? Fine.
Yes. Yes,
Yes.
sir.
Now if I increase the number of radiations here from say 4 to 6, okay, like previously we discussed this out, that if I increase the number of molecules in the path, the number of events will increase, correct?
Yes, sir.
So now if there are 4 molecules in the path, out of 4 radiations, say consider all 4 will get absorbed, and nothing will pass down. Okay, but they have to be in the path, right? If they are not in the path, if there are 4 molecules here, but one is here, one is here, one is here, and the other one is here, only 2 will get struck up with light, and rest of the 2 will pass, although there are 4 molecules. Are you getting my point?
Yes, sir.
So it
Yes.
actually depends upon the chance of light radiation striking the molecules. Now, if I put them close together, that means I am increasing the concentration. You agree with me? When the
Yes, sir.
concentration is more, they are close together, then the chance of the event increases.
Yes, sir.
Yes, sir.
So more amount of light will be absorbed. You agree?
Yes, sir.
Yes,
Putting
sir.
it other way around, if I want to increase the number of events, can I not increase the number of light radiation striking?
Yes, we can, sir.
Are you, Alia, do you agree?
Yes, sir. So the event being absorbance, right?
Right, exactly.
But so then it will, but the concentration is the same
See,
as
absorption, essentially, absorption depends upon 2 entities, right? One is the molecule of your interest, and second is the light radiation striking, correct?
Yes, sir.
So if number of molecules, when they increase, they cause increase in absorption. Putting it reverse way, if the number of light radiation striking increases, will it not increase absorption?
Yes, sir.
Are you getting my point? So does it seem to be dependent upon the intensity of incident light, or does it not?
It does depend on the intensity of light.
Then why you are writing it is independent of the intensity of incident light?
So if we increase the incident amount of light, so and the concentration remains the same, then
No.
wouldn't transmission be more possible outcome instead of absorbance?
No, transmission and absorption are just inverse of each other, correct?
Yes, sir, exactly.
So if transmittance increases, absorption will decrease,
Will decrease. Yes, sir.
right? Yes or no?
Right, sir.
So where you are taking us, Alia?
So you just continue. I seem to be a little bit confused, but I'm sure I'll get it.
Yes, I am actually confusing you so that your basics become very clear.
So what I'm trying to say is, if we increase the amount of light incident, then
Yeah.
and the concentration remains the same. Just say the concentration is lower, then the chances of
Okay.
transmission would increase and absorbance would be low. So it doesn't.
Okay. So you
when
don't believe that absorption and transmittance are inversely related terms with each other only?
So I believe it. I believe in it.
Then how come that can happen? If one increases, the other should decrease, while the other increases, the one we are talking about should increase, right?
Yes, sir.
In the same proportion, that too.
Yes, so they are inversely proportional.
Right, exactly. Okay, let me put it like this now. Okay, because I was able to convince a few of you, but not all, as I can see. So now there were, say, these many radiations coming through. We first understood that how increase in concentration can increase the number of absorption events. So if there are 4 radiations and there are 2 molecular entities involved, then there will be 2 radiations lost and so on and so forth. But if there are 4 molecules, but they are not in the path of light, as I just said, then these 2 radiations will come out as such, and you will miss these 2 events, correct?
Correct, sir.
Right?
Yes, sir.
Now, if I increase the number of radiations here without increasing the concentration remains 4 only. But if I increase the number of radiations striking, say there were only 4 previously, now there are 100. Will they find these 2 other molecules which previously didn't take part in the absorption event?
Yes, sir. There are chances
Yes,
that
sir,
they
there
will
might.
fire.
Yes,
Right.
sir.
So will there be increase in absorption?
Yes, sir.
Alia, now do you agree?
So I do agree.
Okay. Now, as I am now successful enough to convince all of you, let me tell you that this is not the reason, or this is not the actual reason of stating this, that it is independent. It is actually independent of the intensity of incident light. The reason is given in front of you. See, in first situation, you saw that amount of light incident was 100%, amount of light coming out was 50%, right?
Right, sir.
Right, sir.
Now, in the second step, what happened was amount of light incident was 50%, amount of light transmitted out was 25%. What is happening? See, now the amount of incident light is only 50%, right? But the
Yes,
amount of
sir.
transmitted light is still 50% of the original 50%. Are you getting my point?
Yes, sir. Yes, sir.
Yes, sir.
So now what is actually happening? It is not appearing to be dependent on the intensity of incident light. Why so? Is because of this relation. It is a ratio, right? You always see it in proportion with the incident light. You never see it alone. That's what the problem with most of the people is. When we say it is independent of the intensity of incident light, here it means that you need to compare both these things together. You cannot look upon to what is coming out only. If you look at what is coming out only, then it appears that it is dependent, but it is not, because it is a ratio of the two things together. Now is it becoming clear?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right? So it is something like, say for example, it is, as I said, it's a chance event. So you must have seen a dartboard, right?
Yes, sir.
And imagine that I have 5 darts with me, and the chance that I can hit these 5 darts to the dartboard, okay, sorry, not 5, let me make it simple for you. Say the chance of me hitting the dartboard is 50%. So if you give me 10 darts, I will hit 5. Do you agree?
Yes, sir.
Yes, sir.
But at the same time, if you give me 100 darts, I will hit 50, because the chance is always 50%. What my
Yes.
point? So now if my chance of hitting the dartboard is only 2%, so if you give me 10 darts, I will hit 2. If you give me 100 darts, I will hit 50. Sorry, 20. Are you getting my point?
Yes, sir. Yes, sir.
Yes,
So
sir.
is it dependent on the number of darts?
No,
No,
sir.
sir. It is independent.
No, sir. It's independent.
So exactly in the same manner, it is independent of the intensity of light. Okay. Just give me 2 minutes. I'll be back. Okay, so we are good to go ahead from this point.
Yes, sir.
Yes.
Yes, sir.
Okay, so I believe that I was able to convince you both ways. So one way which proves that it is independent of the intensity of incident light, and the other way which doesn't hold good. But one thing that you need to understand is that when we derived the relation itself, it was taken to be a ratio. And when you are talking about a ratio, then you need to consider both the things at the same point of time. So it is actually independent of the intensity of incident light. So now we go further from this point onwards, and we look at some other important aspects. Okay. Okay. Can anybody tell me, when we are looking at this relation, can anybody tell me that what's the role of this proportionality constant, which is also called as absorption or extinction coefficient? Yes. Have you heard about this term previously? Absorption coefficient or extinction coefficient?
Yes, sir. Yes, sir.
Okay. Can you tell me what is this? What is it exactly? So if we look at this relation, we know something about path length, we know something about concentration, we know almost a good proportion of understanding about absorbance, but we don't know anything about this small a. So can anybody explain what is absorption or extinction coefficient? Is it something more than the proportionality constant? Okay, basically, when we look at this relation, it seems that absorption coefficient is absorbance per unit concentration and path length.
Yes, sir.
Okay, what does that mean? That when the path length is kept at, say, 1 centimeter and concentration is 1 unit, say, for example, 1 gram per liter, then whatever be the absorption, that will be equal to absorption coefficient. Is it good?
Yes, sir.
Yes, sir.
But do you think that this is an important term to understand anything about absorption or quantification analysis? Okay, because we are almost to nearing the end of the class, what I will do is that I can write it like this. That extinction coefficient is dependent upon, it is nothing but absorbance per unit concentration and path length. Okay, but we'll understand some more details about this extinction coefficient because it's a very important term. As you will understand in our discussion, perhaps in the next class, that it is a very important term. And if at all you know something about absorption coefficient or extinction coefficient, then you have a liberty of knowing a great deal about or estimating a great deal about the concentration of your sample. Okay, so what I will do now is that I will stop here today because there is only 5 minutes remaining and we cannot discuss much upon absorption coefficient in that less time. So we'll keep our discussion reserved for the next class. Okay, so in case you are having any doubts regarding the portion that we discussed today, you can ask me, or